Hello and welcome to Webinar Wednesday, hosted by the Concrete Preservation Alliance. Good afternoon to our friends joining us from North and South America. Good evening to our friends tuning in from Europe, Africa, and the Middle East. And to those joining us from Asia and Oceania, it's late, go to bed and get some rest. My name is Scott McCullough with Vector Corrosion Technologies, and it's my pleasure to kick things off today and introduce our featured speaker, Mr. Chris Ball. Webinar Wednesday is a series of monthly educational webinars running from August 2020 to July 2021, addressing best practices and new innovations in the field of bridge preservation. Today is the third installment of our webinar series, and we have much more to come, including topics such as non-destructive testing, impressed current cathodic protection, post-tensioned evaluation, and even trenchless culvert rehabilitation. Just one final reminder before we begin, that this webinar is being recorded for the benefit of those who could not join us today. The Concrete Preservation Alliance is a growing coalition of organizations committed to advancing best practices in the field of concrete preservation and infrastructure renewal. Our members are working together to promote concrete education and awareness of the concrete repair industry standards, new and innovative corrosion prevention technologies, and sustainable construction practices. The current members of the Concrete Preservation Alliance are Vector Corrosion Technologies, NDT Corporation, Vector Corrosion Services, and Vector Construction. Our members are concrete evaluation, repair, and protection specialists that are dedicated to saving structures and sustainable thinking in construction. In line with that focus on sustainability, did you know that the concrete industry is the largest user of resources and raw materials, and that approximately 40% of solid waste comes from construction and demolition? Making new structures last longer and the rehabilitation and reuse of existing structures saves money compared to the cost of premature failure, demolition, and rebuilding. In addition to the economic benefits, repairing and extending the service life of existing structures reduces the consumption of natural resources, pollution, and solid waste. The positive impacts of preserving concrete structures can easily be calculated using some basic assumptions and the volume of concrete preserved. WeSaveStructures.info is the digital home of the Concrete Preservation Alliance and your resource for concrete preservation knowledge and information, which includes this handy environmental calculator that is free to use in calculating the environmental impact of concrete preservation. I encourage you to check it out. WeSaveStructures.info if you're interested in more information about the Concrete Preservation Alliance or the upcoming webinar program, I encourage you to visit WeSaveStructures.info. All upcoming webinars and events will be posted in the events tab. And as already mentioned, today's live webinar will be recorded and posted here for your benefit in the future. But enough from me. We're on to the main event, the star of the show, and why you're really here. Let's welcome Mr. Chris Ball, Senior Vice President of Marketing and Sales for Vector Corrosion Technologies. Chris has over 20 years of experience in the construction industry with a specialty in concrete rehabilitation and corrosion protection. He is a member of the National Association of Corrosion Engineers, the International Concrete Repair Institute, and the American Concrete Institute, where he is currently serves as chairman of ACI E706, which is all about concrete repair education. Chris hails from Frankfort, Kentucky, and is also a highly qualified bourbon educator capable of delivering a similar webinar on that topic. Seriously though, Chris is a seasoned veteran of the industry, and today he's here to share his experience in the repair and protection of severely corroded bridge substructures using the galvanic encasement approach for abutments, beams, and columns. As you can see from the photo on screen, Chris really likes to wrap himself in his work. So Chris, maybe start off by saying Chris, here's the photo. Chris, what's going on here?
Well, first of all, I have to make a comment about the bourbon. As being a native Kentuckian, bourbon is in my blood, but not right now at this second. So, but anyway, yeah, what you see there is a photograph. Actually, it was taken in one of our plant, and it's a a preformed FRP jacket that was being manufactured for galvanic pile protection for a project. So surprised how large it was, and I thought it'd be interesting just to hop in for give it some perspective. But I'm not sure where you actually found that photo, but it's very very interesting. But on with, as Scott said, the feature presentation here. And just to start off with a few pictures that I wanted to show of bridge structures and some problems that we've seen. I'm probably like a lot of you guys out there, when I'm driving around the highways and under bridges, I tend to look up and do a pass-by inspection, and these are some photographs that we've snapped through the years. But on the top left, you see a typical bridge structure in an environment where you have de-icing salt chemicals, and you have likely a failed joint, leaking through the joint, leaking down onto the pile cap there, and basically chloride contamination of the structure causing underlying corrosion and spalling. The photo in the middle on the top is one that I like to point out. It's obviously a spalled concrete from corrosion, but you can tell from the picture that the coating that was applied to the column was applied prior to the spall occurring. So while coating may provide some aesthetic and maybe some protective benefits, it's not really addressing the underlying corrosion cell. And then you also, on the top right, you see an epoxy coated rebar structure. It's really more common in North America. Obviously, they're not perfect solutions and have corrosion as well. And then the bottom right here, something that when I looked at this structure, I see it's a repair that's failed, and you had underlying corrosion issues. You can see the weld-to-wire mesh in there. It's a shotcrete repair. And the shotcrete repair itself did not address the corrosion issue and had a limited success at that point. And then on the bottom left is the all too familiar to many of us. It's basically ongoing corrosion on a bridge deck. You see several generations of repairs that have been completed, and becomes a patchwork quilt of repairs. And then you see a couple more that are marked out for future repair. So in this situation, I would say the repair itself is probably not failing, but the repair is not addressing the overall corrosion issue. So the objective really, whether it's the topic that we're talking about today, galvanic encasements, last month we talked about discrete anodes, and we have more topics coming up. Each one of these many of these are designed to provide different solutions and options to deal with corrosion issues on existing structures to extend the life of repairs. So when we're talking about the corrosion, it's in cathodic protection, which is where we're headed. I always think it's good just to do a quick review of the corrosion cell in concrete. And if you can imagine that you have your reinforcing steel that's placed on your forms, and you have concrete that's placed around the reinforcing steel. You have a little bit of initial corrosion of the reinforcing steel, but that corrosion is in the alkaline environment of your Portland cement concrete, and that creates a passive film on the steel. And so your steel is going to be happy and very satisfied and passive in that environment for many years until something occurs to break down the passive film. And in this situation, what these hatched lines are illustrating is the progression of and diffusion of chloride ions into the structure. If this is a bridge deck in a northern environment, it could be the same situation. It could be a column in a marine environment, but you have an external source of chlorides that are working its way down to the reinforcing steel. But once you get to a point where there's sufficient chlorides present in the concrete around the reinforcing steel, it starts to break down this passive film, and corrosion can begin to occur. In the areas where you have active rust formation is basically the areas where you're losing electrons from that section. And that's basically causing a dissolution of the metal, and effectively it's reverting back to its earlier state before the energy was applied to create the reinforcing steel. So electrons flow to other areas of the structure, which we call the cathode. This area is the anode. The other sections are cathode. The cathodes are part of the corrosion cell, but they are actually the area, the net, they're receiving the current from the anode. So, and then to create the corrosion cell, you have what we call ionic current. It basically it flows through an electrolyte, and in a situation with concrete that's concrete that has sufficient moisture in the concrete for this to be conductive in this situation. So once you start to get a sufficient corrosion occur, the steel corrosion byproducts expand and create cracking in the concrete, because concrete's weak in tension but strong in compression, and that's why we put the reinforcing steel in the concrete in the first place. So you're starting to create tensile forces and cracking, which eventually leads to delaminations and spalling, and if it's not addressed, can lead to structural issues. So a couple other pictures here. This is a pretty severely corroded beam, and you see, widespread corrosion. Like I said, starts off as delaminations, eventually spalling off the structure itself. And then, just to point out too, with chloride contamination, there are other methods of corrosion, such as carbonation, dissimilar metals, etc. But chloride contamination is pretty aggressive to the reinforcing steel and can cause this severe pitting corrosion, which can be a structural issue. So that's a little bit of the background on a quick review of the corrosion cell. But then we also have the secondary issue that occurs, which I referred to with the patchwork quilt of repairs on the bridge deck in one of the previous slides. And this is just an illustration that shows what happens potentially when you are doing concrete repair. And so the area of the concrete, it says the chloride-free patch. Obviously, this was the area of the initial corrosion, which was the anodic site. You've chipped that out. You've done a good quality repair. You've cleaned the reinforcing steel, come back with the chloride-free repair material. And now, if you have sufficient levels of chloride still remain in the surrounding areas, you have this abrupt difference between chloride-contaminated concrete and chloride-free concrete. And effectively, what you're doing is forcing the corrosion cell to reverse, where the last place in the structure typically it wants to corrode now is this passive steel in the repair. And the other area, which is maybe not corroding before, but now it's very corrosive relative to the repair, that's where you can start to see new corrosion activity form. So this is a bridge structure, actually in a marine environment, and you see the original repair. You see a secondary repair around that. We hear that referred to as ring anode corrosion or incipient anode formation, and then you see new areas that are formed that are marked off for another round of repairs. So we need to repair the structures. We want the structures to last longer. So, but when we need to repair and rehabilitate a structure, and we want to probably look at what are the options if corrosion is the cause of the problem. What are the options that we might want to look at to extend the life of not only the repairs but the overall structure? So there are many different options, and we're covering these topics in different seminars that we are having through our bridge preservation webinar series, the Wednesday webinar series. But the first one, just to mention, is electrochemical chloride extraction. That's a temporary treatment where we're impressing a high amount of current onto a structure with the intention of reducing the amount of chloride in the structure and passivating corrosion activity. And that's the photograph that you see on the right here is one of the signature projects that was done in 2007 with the Arch Bridge in Idaho. Ended up being project of the year for the International Concrete Repair Institute. A variation of that, which many of you guys are familiar with, will be compressed current cathodic protection. It's effectively similar to chloride extraction, but it's a permanent system. that's installed and has electrical current that's applied to the reinforcing steel by inert anodes that are designed to last over time. Then we have localized protection. We addressed that, as I mentioned in the last seminar, with Dr. George Sergi, talking about the 20-year history of type 1 anodes and how they're used for localized protection. We can also look at targeted protection. I know in December this is going to be a topic where we say, well, you don't have to protect the entire structure. Let's potentially look at areas of high corrosion risk. And we can use what's referred to as type 2 anodes or fusion technology there for targeted protection. And then we have just in generally speaking, galvanic cathodic protection as a category, which today we're going to be talking about the galvanic encasements, and as a ancillary topic that would be overlays. We'll get into that in a second, but also surface applied systems such as arc spray zinc metallizing. So just, you know, those are the general options. Now we're going to narrow this down a little bit and look at galvanic protection. And to start off with understanding what galvanic protection is, we probably need to have an understanding of dissimilar metals and where they fall on the galvanic series. So each metal has its own kind of a natural electrical potential. And depending on where the metals fall on the graph, you have metals which are more anodic or more active metals, and then you have metals which are more noble. And so once you connect two of these metals together, you're setting up a dissimilar metal corrosion situation. And the one that is less noble will become the anode, and the one that's more noble becomes the cathode. So just as an illustration here, you see this is two Petri dishes with solution, and you have zinc on one side and copper on the other. And then you have what they call a salt bridge that goes between. So now you have an electronic connection between the two metals, and you have that ionic path that we talked about originally. In this situation, instead of it being through the concrete, it's through this salt bridge. And that sets up your little corrosion cell, which in this situation, zinc would be the more active metal, copper would be the more noble metal. And so therefore, copper wants to become the anode, zinc wants to become the cathode, zinc wants to become the anode, and you have this corrosion cell that starts to occur. Now, when you start to talking about concrete, we can use that same philosophy, dissimilar metal corrosion, but we're using it in a positive way to provide protection. And that's what we call, or it's called generally galvanic protection or sacrificial protection. You have your reinforcing steel and concrete. It has a range of potentials. You know, if you ever do a half cell corrosion potential survey, it'll generally fall somewhere in this range. Could be outside. That's a common range. But if you measure the potential of zinc, it's much more electronegative than the steel in concrete or even in chloride contaminated concrete. So we go back to the same type of setup. We have zinc that's connected to the reinforcing steel, which is in some type of environment in the concrete. The zinc, as we showed here, is more electronegative. It's going to provide, it wants to become the anode, the steel becomes the cathode. The zinc provides sacrificial protection to the steel, and that's what we refer to as galvanic protection. So how do we do that in concrete? We talked about zinc. Zinc's common what is used to provide galvanic protection. But what we find is that if we just use a piece of bare zinc, you can take a zinc ingot and put it, connect it to the reinforcing steel. You can cast that in concrete. You see on this chart here that you have this is the corrosion rate of zinc by pH. So when you get into acidic areas, the corrosion rate zinc is high, but when it's in this section up to pH of 12.5 or so, or a little higher, zinc is very passive in this environment. And then, so we know that the pH of concrete itself is somewhere in the 12 to 13 range. And so the zinc anodes are going to be very passive in concrete. So to make an embedded zinc anode operate, we need to create a higher pH environment around the zinc artificially, and we push that environment up to a pH of 14 plus, and that is corrosive to the zinc, or keeps the zinc from passivating, but it's not corrosive to the reinforcing steel. And this allows the anode to be active over time. So the first demonstration of this was in the late 90s with the original embedded galvanic anode, which I mentioned George talked about last month. But there you have your sacrificial metal core, this active cementitious matrix, which is effectively high pH environment around the steel that's connected to the around the zinc, that is connected to the reinforcing steel through the tie wires. And then once that occurs, Mr. XP uses the magic of electrochemistry to provide corrosion protection. So going back to our previous illustration of the repair, we saw that, in this kind of scenario, you can start to see new corrosion activity occur outside. Now you're seeing, you connect the anode, which is more electronegative, in the repair. So now the repair area where the anode is going to be more anodic relative to the areas outside the repair. And so what ends up happening is that you have localized areas of protection where these type 1 anodes are installed. And you see this on this bridge itself, just providing, it's not protecting the whole structure, just localized repairs. They have localized areas of influence. So other applications, for these types of anodes we talked about before, you can use them for joint repairs, where you have anywhere we have new and old concrete. One example here is bridge widening. You see the anodes installed right at the interface between the new and old concrete. And we also have seen these types of systems utilized in new construction. There's a bridge deck that has anodes installed. So, once we discovered that, okay, we can make anodes, put in the repairs to make the areas around the repairs last longer, then we start looking at where else, there's other obviously sound areas of concrete that are still, they may be sound at this point, but they're still corroding. And so to devise a corrosion control system that utilizes these embedded anodes, you basically can use the same type of system put into drilled holes. This is a precast box beam that has a drainage issue. You have chloride laden water running over the side of the beam, and that just is causing this localized corrosion. But rather than just protect the repairs, these types of anodes are installed into drilled holes on a pattern throughout the repair and into the sound concrete to provide, to reduce the rate of corrosion. So we start to look at it one step further. If you can visualize the corrosion control anodes put into drilled holes, and all of a sudden the typical spacing might be, 2 feet spacing or something like that. You put into 1 feet, you go down to 6 inches. The anodes get closer and closer, and they start to form a line. So that's when we start thinking about, well, is there a possibility? Can we make larger anodes? And so when we start to develop the distributed anode system. So these anodes are made up to 2 meters in length. They have a larger anode, has a larger area of influence. They basically are put across the structure, typically to provide large areas of protection. And because they're larger anodes, they have a higher current density. They can provide a higher level of protection. We can change the spacing or the amount of zinc in the anode and really provide a long-lasting galvanic protection system with 20 to 40 plus years of service. So this is around 2003 when we started to look at these types of anodes for distributed protection, and this is a bridge deck in Ontario, which I'll come back to in a second. But that basically, see the anodes distributed over the entire area to provide global protection. But this is this is not a bridge, it's a plaza deck, but it's a good illustration of how you can also use these types of systems just to protect high potential areas. So there was a corrosion potential survey that was done on this plaza deck, and these anodes were just installed in the areas where they have high potential. And in both these situations, a concrete overlay was placed over top of the anodes, and obviously they're connected into the reinforcing steel. So going back to the bridge application, this is the first bridge deck overlay that we did years ago. And these anodes were, they're fairly large, they have a lot of zinc in them. And we actually embedded them onto the deck surface. And then just to provide extra crack control, there's a carbon fiber grid that's placed over top of that for provide crack control to the concrete. And this was the first pilot installation, and it's still being monitored 17 years later by the Ministry of Transportation. And you see, a whole bunch of numbers here. They may not mean a lot to everyone, but effectively you're measuring the amount of current that's being generated by the anode to the reinforcing steel. And you see that's relatively steady. Typically you might see a decline a little bit. But the polarization is a measurement of how much current goes to the steel relative to how the corrosive the environment is. And typically people are looking at, if you have more than 100 millivolts, you are generally meeting accepted standards for cathodic protection. So the most recent data was collected in 2020, this summer. It's not on the chart here, but the steel is still cathodically protected. And while the current density has dropped a bit, it's still over 1 milliamp per square meter after almost 17 years, which is definitely in a good corrosion control mode. More recently, we still get involved in these types of applications where we're doing overlays. And this is a newer version of the distributed anodes, a little bit smaller. You see them kind of placed end to end through the area after hydro demolition. And then the sound concrete areas, you have some slots cut where the anodes will continue on. And so, once these anodes are installed, they're connected to the reinforcing steel. The concrete overlay is placed. And in this situation, you had a asphalt membrane and a waterproof membrane and asphalt wearing course that was installed on top of that. So you have a galvanic overlay. A little bit later, we started looking at other applications where they're installed. These types of distributed anodes can be installed even in longer repairs. And this is the bottom of a pile cap in a more of a marine structure, as you can see. And you have the bottom 6 inches of concrete was removed because of how the proximity to the water. There was a lot of corrosion. See 2 rows of distributed anodes placed end to end, and then it was completed with form and pour repairs. And then in 12 years later, the structure is in good shape. You're providing corrosion protection primarily to the bottom of the beam, which is closest to the water. So back to galvanic encasements, which is really the topic that I want to cover. It kind of starts off with overlays, but then we start looking at true encasements, and they can be come in many different shapes and sizes. And one of the early applications that we see for this was for abutment repairs. And this is a typical type of design for a slab bridge, where you have a joint that's over top the abutment. As we know, joints are the big maintenance issues. You have the water leaking onto the top of the abutment, and then you see that sufficient chloride causing corrosion of the abutment. So the deck itself may be in relatively good shape. Maybe you have some localized corrosion here, but it's starting to affect the abutment itself, which is load bearing for the structure, obviously. And so, Ohio DOT looked at many different options. Obviously you could do nothing. That's not really feasible, particularly on an interstate highway. Like this, many of these are along I-75, if you're familiar with the area. You look at repair, and they did some repairs, or you can replace the bridge or replace the abutment. Obviously those are more comprehensive options. And so when you start looking at repairs themselves, it has to be temporarily supported. They may replace the abutment. Obviously you have traffic control, but anything they can do to keep the bridge from being posted is obviously a real benefit to the traveling public. So Ohio designed a repair solution, which is effectively to create a reinforced overlay, or as we would call it today, an encasement on the face of the abutment. And so you basically build off the footer, you build an additional face to the structure, and support the existing slab. And you see this picture here. This is one of the early ones where, you see the corrosion activity and the spalling of the concrete. They've installed, in the process of installing some new reinforcing steel. And then these early ones, they actually installed some of the type 1 anodes, which would help provide some localized protection. But ultimately, in this kind of scenario, you want a long-lasting repair, so you want to provide protection to the entire abutment. So this is where you start to see the distributed anodes being used in the galvanic encasement across the entire abutment face. So you see the 6-inch reinforced, effectively a new wall in front of the old abutment. And these anodes are connected into the reinforcing steel to existing steel to provide localized protection. So just to walk through a couple photos of repair that employed this method. You see, leaking, and obviously some rust staining and efflorescence. In this situation, you're removing the existing concrete damage, and then installing dowels to effectively connect the new reinforcing to the concrete, but those are also used to allow the anodes to sit in this overlay area. And so you see these long anodes, these are over 7 feet in length, and they're placed end to end. So these anodes, these are alkali activated anodes, so you actually have zinc inside the active cement matrix. Have a couple of different wires come off. They are all interconnected, and then they're also connected into the existing black bars. And because this is one of the first ones that was done by Ohio, they've done dozens, if not hundreds, of bridges since then. They wanted to monitor the anodes to see how they work and what kind of level of protection and service life they could achieve. So a few anodes at the end of the abutment were not directly connected to the steel, that they basically run up that conduit there into a monitoring station where you can see the data loggers that are measuring the current and the temperature within the concrete. And you see the reinforcing steel that's been placed. The anode spacing can be varied. If you have a lot of reinforcing steel or more corrosive condition at the top of the abutment wall, you can have a tighter spacing of the anodes. And then when you get into lower levels of reinforcing or lower levels of contamination, the anodes can be spread out. Then the forms are installed, and then your form and pour repair or pumping repair is complete. In this situation, they use self-compacting concrete, and you see this new wall that's been placed in front of the old wall, and effectively, as we mentioned, the galvanic encasement of the abutment. And then you see the completed repair. Also went back this summer, and 15 years later, it's still in good condition. So we mentioned a little bit about the monitoring with data loggers and battery-powered data loggers, taking regular measurements, anode current and temperatures, etc. We can start to plot out two things. One is the level of performance of the system, but also like you can start to estimate the longevity of the anodes. And so here you see the galvanic currents in blue. And so you see the readings, and then we have periods where the battery died. And then the temperature readings, and you see this is in Ohio, so it's in the northern part of the US. You see it, in the summer, average temperatures, and in the winter, there's a lot of variation. And you'll see the anode current, because it's a galvanic system, will vary based upon that. So you have good 10 years of information there. But as I mentioned, we went back and took some readings 15 years later in this fall, and the system is still performing. You're still getting high levels of polarization. Your instant off readings are fairly high, which is indicative of high level cathodic protection. And as I mentioned, is you can measure or estimate the anode or the zinc consumption based upon the current generation. These anodes are going to be lasting, well over 35 years, which is substantially longer than the original design, and obviously the structure is protected. So that's kind of a repair of an existing structure. The deck itself is going to be maintained in place. Here's an example of the same type of repair, but it's used in conjunction with accelerated bridge construction techniques for repair. So if you see the picture on the right here, there's a lot of concrete damage in the deck. And eventually, the decision here was okay, we're just going to replace the superstructure on the bridge. But in order to do that, it's more cost effective, works better for the schedule, less disruption, is to see if you can reuse the substructure, and in this situation, the abutment walls, which they were able to do. You see some surface preparation on the wall there. You see it's a little hard to see, there's the galvanic anodes. Once again, a new layer of reinforcing over the wall. So just like we saw with Ohio, this basically a galvanic encasement of the abutment was done to provide long-lasting protection to the abutment. And once again, the anodes are interconnected. They're connected into the reinforcing steel. And then over the weekend, the new decks were built in an adjacent area. When everything was ready to go, the abutments were repaired. They basically lifted the old sections out and brought the new sections in and had the traffic up and running over the weekend. And this would be obviously a much longer process if we had to rebuild the abutments in this situation. There's your final look on the structure. You have the same situation here with the readings. It was monitored. You see a lot of variation in current with temperature, but the system's still performing well. Just a little bit different example here also, which is more of a beam kind of scenario. This is the Wade Bridge in Harrisburg, Pennsylvania. You see the details. This fairly large repair project that was completed in 2009 or began in 2009, which included repainting the steel structures, etc. There's a series of piers around the over the railroad tracks where they had severe deterioration of pier caps. You see the level of corrosion that's occurring, and because they are around the train tracks, they're it's a difficult environment to work in. They want to have a long-lasting repair. So the owner here selected the galvanic encasements as an preferred option, and then but in the columns and the abutments, which were still contaminated but not necessarily as advanced in the corrosion, they employed an arc spray zinc system with humectant. So this is the beam repairs under progress. Once again, you have the spalled concrete that's just basically being removed. You have the embedded distributed anodes placed along the beam, and then the engineer designed basically a structural cage of steel to go around the beam itself, and then you had some anodes at the end of the beam. And then you see, basically they had beam anodes on the bottom side of the beam too. A lot of times you'll have, as you know, a lot of additional reinforcing steel at the bottom of the beam, so you may need larger or more anodes just to protect that amount of steel in the bottom section. And then you see the form work that's been installed, and that's going to be cast in place. You're basically effectively enlarging the beam with a structural encasement that also provides corrosion protection. As I mentioned, they also did some surface applied protection on the lower sections of the structure. We'll talk about this at a later time, but effectively you're melting zinc, spraying it on the surface of the concrete. That zinc's connected into the reinforcing steel as well. It has a humectant solution that's sprayed onto it to improve the performance of the bare zinc. And so it's basically a sacrificial coating system. So another more recent example is this is also accelerated bridge construction, is the Gardiner Expressway. You see once again the details here. I don't have to read through them, But once again, you have de-icing salt chemicals causing severe corrosion of the reinforcing steel. You see, it was all in the news, several different articles if you search for online about falling concrete. I thought this was kind of interesting. It says, well, only 25% of the falling concrete is from the Gardiner. Well, whatever the percentage is, it creates an unsafe and unsightly condition. So they looked at lots of different options on what to do. This is a major thoroughfare that goes into downtown Toronto. And if you've ever been there, it's very heavily traveled. So they looked at even taking the elevated highway down to the ground level, should make a tunnel. They ended up coming up with a hybrid plan, and as part of that plan, included rehabilitation and replacing the deck and girders of this section here between Jarvis and Cherry Street. And that's going to be done with accelerated construction techniques. But in that same situation, they wanted to repair and protect the substructure so it has a similar service life as the new deck. And to do this, once again, a galvanic encasement was selected. And you see a little bit of a drawing here. You see the anodes basically distributed around the concrete surface, and then a new face installed. There's a drawing that shows the layout of the anodes, the green lines. You see some vertical. In this situation, it just was not the beam, it was beam and the columns. You have the vertical anodes on the columns, the horizontal anodes on the pier cap here, and then once again, in this situation, they had a welded wire fabric grid placed over top of the anodes. Here's a really good picture I thought was interesting. You see the level of deterioration on the structure kind of throughout all these different pier bents here. Here they started off with the column repairs. So the column repairs already have the galvanic encasement, and they're starting to do the concrete demolition on the top. As we progress, you've got your formwork here for the columns. Now on the pier caps, you have the distributed galvanic anodes, which were installed, connected into the existing reinforcing steel. And then you have, as I mentioned, this welded wire mesh. So the anodes are designed to protect this steel. The steel is still partially embedded in, or a substantial amount of it is still in chloride contaminated concrete. So they wanted to have at least a 25-year life of the substructure, and the galvanic encasement was able to achieve that. You have this picture that shows the end of the beam. It's already been repaired, has a new concrete cast. And this section is ready for the next repair. And then you see the same thing here. You see the video is taken, it was just kind of more of an action shot. You saw the repaired section, the section with the galvanic anodes and the welded wire mesh installed. And down at the end of the beam, you still have areas that need to be prepared for the galvanic encasement. So, going back to what Scott talked about in the beginning was the rehabilitation of the pier. 25 plus year service life extension. You can go out to the We Safe Structures site, to the environmental calculator, determine how many cubic meters of concrete was maintained in place. That equates to a certain amount of reduction in carbon dioxide pollution and other pollutants, preventing materials, solid waste, from going to landfills, and also eliminating the use of potable water. And there's some comparison information for there. So I encourage you to go out and look at the calculator. So we talked about several different examples here. These are all de-icing salt chemicals situations. Here, this environment is actually a marine environment, and you can have the same thing. This is Florida DOT. Here you have the use of some metallizing back on, this is in the Keys. It's a very warm, humid, high chloride environment. The metallizing just wasn't enough to provide the service life and protection that they looked for. So as many of you guys may know, galvanic jackets are used very commonly in Florida for pile protection, but those are in the pile sections that are submerged and extending out of the submerged sections. In this situation, these columns are actually above the high tide, so they are not in any submerged situation except maybe during a storm event. So you have another situation here. You had an existing jacket that was on the column. The jacket was removed. It did not have cathodic protection. You saw some ongoing corrosion underneath, and those are going to be replaced with a galvanic encasement, or in this case, instead of using additional reinforcing steel, we're basically using a stay-in-place forming system. So you see the anodes installed here. With the continuity groove, you basically have an opportunity to chip in, expose all the vertical bars, make sure all the steel is interconnected. And this is epoxy coated steel in this situation. So you want to make sure that they're all bonded together so you get good electrical continuity of the steel within the structure. And then after that, you see an FRP jacket installed with some bracing, and that's basically there to hold the concrete or the grout that's placed to fill the annular space. Those jacketing systems can come in a couple different forms. Probably most common right now is to use an FRP jacket. These are preformed shells. That's the jacket that I was emerging from in the photograph that you saw about 45 minutes ago. But and these are preformed shells. These are fairly large columns, so they came in four-piece sections that were put together in the field. And you have the seams which are sealed. The other option is to use a modular PVC forming system, which come in smaller planks that are assembled in the field. It's much lighter and easier to use, and also functional as far as a stay-in-place forming system. But you see here, this is Niles channel, and it's the original installation for this type of system for Florida DOT, and we set it up to monitor. On this box, you have the anodes coming up to a switch. You have the reinforcing connections up, and then at that monitoring box, you can measure you also have a reference cell in there. You can measure current and potential that's of the jacket system, and obviously very similar to the other numbers. Have a high level of protection, and they were very satisfied and have moved forward with engaging this type of repair. So just we started off talking about overlays. We moved to encasements on a beam. We talked about using additional reinforcing steel so that you can become it's kind of like a one-step repair protection option that can also incorporate additional reinforcing. We really have a need to use the alkali activated, distributed anodes within the structure, so they're self-activated. Been doing this for a while now. We have, since the early 2000s, as I showed, we've demonstrated high level protection, and that these severely corroded structures, which in the past may have been considered good candidates for demolition and replacement. Now, maybe there's a possibility that we can save some of these older structures. And like we said, in addition to, shortening the construction time, maybe reducing disruption to the traffic or the public, we do use less concrete materials and other services, but we can also extend the life of the structures. It's not easy. It's a challenge. It's an investment, but it is. If we make it a priority, it's possible, and we can have a positive impact on not only the civil infrastructure, but also making the structures last longer and having sustainable benefits. So with that, I appreciate the opportunity to talk with you today. Just looking at the clock, we'll have some extra time for a few questions, and I'll just turn it back over to Scott.
Thanks, Chris. Well, if there's one thing I know about bridge engineers, it's that they love nasty photos of spalls and rust-stained bridges in various states of disrepair, and your presentation had that in spades, so thanks very much. We have been peppered with questions over the last little while, so we will only be able to get to a handful right now. Are you ready?
I'm ready. Lay it on me.
A couple for clarification, just right off the hop. Are chlorides the main culprit in all the case studies you showed, or were there different deterioration mechanisms?
Yeah, in this situation, these were all chloride-induced corrosion problems. And, as we talked about a little bit at the beginning, the chloride induced corrosion is really the most severe type of corrosion, and it's progressive. Once it begins, the chlorides are in the structure unless you try to take them out with chloride extraction or whatnot. It's progressive and it's very, very severe. When you have carbonated concrete is another corrosion mechanism. And that you can have corrosion of the reinforcing steel without chlorides. And but then in that situation, what's happened is that you've lost the protective alkalinity that the concrete provides to the reinforcing steel. And that's basically by exposure to the atmospheric carbon dioxide. And over time, that concrete loses its pH. And if you lose the alkalinity in the concrete, it doesn't support the passive film anymore. So you can have that situation occur, but what you generally find is that the corrosion activity from carbonated structures is not nearly as aggressive, and many times it's just localized where you might have lower areas of cover. So in this type of scenario, I would say majority of those structures are going to be chloride contaminated. Understood.
Okay, so there was some confusion, I guess, about epoxy coated bar with anodes because of the Ohio case study that you showed. Can you speak to the use of anodes with epoxy coated bar, how to install them, the frequency of connections, and maybe just that case study specifically?
Sure. So, it's always a question that we get because in that scenario with Ohio, and you saw the same thing with Ontario, they use as kind of a standard epoxy coated steel. So on these new sections, they use their standard reinforcing steel kind of detail, which is epoxy coated steel. And in that scenario, the anodes are only designed to protect the steel that's remaining, the black bar that's in the old bar that's in the existing structure. Now, having said that, it would be probably equally as good or maybe preferable to just use black steel like you saw in the Pennsylvania example. And in that situation, you can tie the new steel in with the existing anode system, and those anodes will provide cathodic prevention to the reinforcing steel, the new steel, while it's also helping to control corrosion in the old bars. So that's kind of describing that situation that we saw on those case studies. Now, when you get into repair of existing epoxy coated structures, that's when we're looking at the last example we talked about was Florida DOT. They no longer use epoxy coated steel, but do have some older structures that have epoxy coated steel, and those structures were the ones that we were putting the galvanic jackets on. And because you do have epoxy coated steel within the structure, you're just not as certain that you're going to have a reliable interconnectedness between the embedded steel. So and you saw a little continuity groove. And basically, you're going to have to expose the steel, just remove a little bit of the coating off the bar, and then you check for continuity between the bars. And you may get continuity, you may not. If the bars are not continuous, you basically just bond them in with the other bars and make that interconnectedness, and then you have a reliable system. So what's happening at that point is that once those anodes are connected to this grid of steel, it's kind of like a pipeline, where in the pipelines they use cathodic protection. The cathodic protection is used in conjunction with coating. So the coating is a primary protection, and then if you end up with holidays in the coating, you have the cathodic protection that's providing protection in those areas. And in that Florida example, that would be the similar thing that's occurring there. the areas where you have corrosion that's occurred or holidays in the coating are getting the protection from the anode. If the coating is sound and intact, those areas would not be receiving protection, but they probably don't need it.
Awesome. Just a question about service life. So what kind of service life can you expect from any given galvanic anode, and how do you determine what that service life is?
So there's kind of two things I think about. One is service life of the anode, and then you also can look at overall service life of the structure. So when we are looking at a galvanic encasement in particular, what we do is we look at how much reinforcing steel there is to protect, how active the corrosion is, and then we design a sufficient amount of spacing and distribution of the anodes to get the amount of current to provide protection. But then we also can size the zinc mass to ensure that we achieve a certain amount of service life. What we find out typically is that over the years, we probably have over-designed them, in all fairness. You know, that the Ohio DOT structure was going to be the anodes themselves were lasting 35 years. They were not designed to last that long. But what ends up happening is when it's highly polarized, and the current starts to drop off, and the anode consumption slows down. But if you wanted to do a 10-year system or a 40-year system, it's possible. You just have to have sufficient amount of zinc to achieve that.
Great. Just time for two more questions here, and we have a couple more coming in last minute here. What criteria would you recommend someone use in deciding between, say, localized repairs with smaller anodes or employing a galvanic encasement method like you've shown with these large strips?
Yeah, I mean, that's a great question, and it's something that these are all options, you know, and every situation is going to be different. You're going to have economic considerations, service life considerations. Those are big things to look at. More from the technical, you know, kind of standpoint, really what you start looking at is how widespread is the contamination or the corrosion that you currently have. And, you know, the way you do that, you can make judgments from visual surveys, but the best way to do it is to really do a little bit more, and you can do this on more of the major structures that are looking at rehabilitation, is to do and invest in a corrosion and concrete evaluation. And so in that you will have a better idea of like how severely chloride contaminated the structure is. That's one part. But the second part that I think is really important is how widespread is, not just the magnitude of corrosion, but how widespread is the corrosion. If it's just really localized and it's at the top of the beam, you know, then maybe some localized repairs with some anodes, maybe in the repairs might be sufficient. But if you have widespread corrosion, then you may need to go to something more like a galvanic encasement. And I really encourage you to come back in December for the webinar in December, which is more going to be focused on targeted protection, because that's this intermediate area where we're not just protecting repairs, we're not going to protect the whole structure, but we can utilize the information from a corrosion potential survey to target the hot spots and to more cost effectively use your corrosion protection budget to make the overall structure last longer.
Great, and this is one question just came in near the end. This is the last one, but I really like this one because it kind of focuses on proper practice. What are the challenges or common mistakes you see made when designing or constructing these galvanic encasements that causes failure or poor performance?
That's a really good question. I think the first thing it kind of goes back to my statement before about you know, having an understanding of what's going on in the structure. We need to have a understanding of the amount of reinforcing steel in the structure. So if the structure is more heavily reinforced than we think, then the anodes theoretically could be undersized for the amount of steel to protect. The other thing that we you see, it's really important is to have a good connection to the reinforcing steel that's durable, and we have some methods. There's different methods to do that, but on most of these galvanic encasements, in these more substantial projects, you'll see the owners call out in the specifications that the contractors will enlist and hire a NACE certified rep from the anode manufacturer, and so they're on site along with the contractor to do initial training and quality controls to really have an understanding that for the owner to have a peace of mind that the system is being installed as best as it can be.
From Anonymous, can galvanic anodes effectively protect structures with coated rebars? Will sacrificial anodes, cathodic protection, induce problems like cathodic blistering in coated rebar systems?
Yes, they can effectively protect epoxy-coated structures, and we saw that actually on the last case study that I showed for Florida DOT. The epoxy-coated steel from a repair standpoint prevents some additional considerations. When we're connecting a cathodic protection system, and whether it's a galvanic system or an impressed current system into a structure, we're relying upon the steel within the structure to be interconnected and what we refer to as electrically continuous, because it's not practical to connect to each individual bar. So with epoxy coated steel, because you'll have some insulation of the steel between individual bars, effectively what we'll need to do is to ensure that each bar is bonded into the system, and you can do that with a series of continuity grooves. So where you can basically cut down, you expose the surface of the bar, remove a little bit of coating, and then you test in between the bars. If they're not electrically continuous, then you can put a small piece of steel in there and weld them together. Once the epoxy coated steel is interconnected, then the anode system is protecting the steel. If there is coating situation on the bar, then the bar is going to be isolated from the anode system. But it's kind of like a pipeline where, if you're in a pipeline, they use coatings on pipelines and cathodic protection systems, and the cathodic protection system is effectively a secondary protection that's protecting where you might have holidays in the coating. That's similar to what's going to be happening with epoxy coated steel with the cathodic protection system like we showed. So there are additional considerations.
Awesome. Question number 2 here was, do you need to clean off the rust from the existing rebar prior to installing anodes at the construction joints or at the interface? I think this is related to the abutment case study you showed.
Yeah, so anytime where you have exposed steel, I would recommend cleaning the bar. Obviously, you can't clean the bar when it's embedded in concrete, and it still may have corrosion there in those locations. But where you have an exposed bar, the most common in practice, for repairs is to chip behind the steel to completely expose that, and then to sandblast the corrosion product off the steel. You're not only removing the corrosion product, but you're also removing cement, which may have some chloride on it. And so that opens it up, and it allows those bars to be well bonded back to within the concrete mix. So it'd be the same situation where you have, even when you're doing a galvanic encasements, many times you'll see that more aggressive surface preparation step may be skipped, and they may just be removing the deteriorated concrete. But even in those situations where you have partially exposed steel, I would still prepare that, and those would be locations also where you could potentially make your anode connections into the steel as well. Excellent.
Question number 3, Are all reinforced concrete coating systems system options compatible with distributed anodes? So this is related to membranes and coatings for the concrete. Would they adversely or beneficially affect the effectiveness of the system?
I would say the biggest, there's not going to be really a negative kind of situation if you are using coating, surface applied coatings, and whether it's acrylic or other types of membranes, if you're getting into the bridge decks or whatever. There's a benefit. You can say there's some synergy there where you can have effectively a drying of the concrete by keeping out liquid water, and also preventing future chloride contamination. So it has an overall positive benefit. If the structure is drier, you may see that the current and the corrosion may be reduced slightly, but whenever you have a situation where you have penetrations in the membrane and moisture that penetrates into the structure, those sections, the anodes will automatically become more active as well. So I would say there's a synergistic effect, but in most cases, particularly when you're getting into abutment and like this galvanic encasement of the substructures, you don't see more commonly a coating system applied. You're just relying upon the cathodic protection system to function.
So it's more like a belt suspenders approach for bridge decks. Okay, excellent. Which is the most important data to collect or to rely on for performance, the 100 millivolt polarization or the current flow?
Well, it's an interesting question. I would say that they're both very important in that, so the polarization of the steel is caused by the amount of current that goes to the reinforcing steel. So when you're getting into these larger, more substantial systems, we've shown that you can achieve what we would call like a full cathodic protection according to the standards, and which is not only the 100 millivolt polarization, but it also can be determined by an instant off reading that's more negative than 850 millivolts. But at the same time, it's also really important to measure the corrosion current that's generated, or the current that's generated by the anodes. And there's a couple of reasons for that, in my opinion. One is that even if you're getting polarization that may be 80 millivolts or 120, whatever, you're seeing a level of protection, and you can measure the current density to the steel, which will give you an indication of the amount of current that the anodes is generating, and that's an important consideration to see if you're not in a full cathodic protection mode, are you actually falling in a corrosion control range of current. The other benefit of monitoring the current, and particularly if you're looking at some of these early projects, and I go back to the Ohio DOT example, you have a design. So an engineer will come, the DOT, and they'll say, hey, we want a system that has a 20-year life. And so you're making some assumptions, and based on experience, you're designing a system. And you can wait 20 years and see what happens, but also you can, if you're measuring the current that's been generated over time, the amount of generation of the current is directly related to the amount of zinc that's being consumed. And so you can begin to estimate the anode service life earlier on in the process by monitoring the current.
Excellent. So this is an interesting question, more about what approach to use in any given situation. Can you clarify what conditions typically indicate that cathodic protection would be beneficial, as opposed to, say, only repairing any delaminations or spalls, and what type of testing was needed to establish these conditions?
I would say, obviously, you always have an option to just do a repair and not include cathodic protection. But if you're doing the testing up front, and the testing, is typically a condition assessment that would include concrete samples to look for the level of chloride. You typically would look at a distribution of chloride by depth into the structure, and you can use that to have if you get into a more substantial kind of review of the structure, you can use the chloride profiling to do some service life estimation of the structure. So if your service life estimation is showing that the chloride penetration is such as limiting the service life, then I would definitely consider cathodic protection. If you're leaving chlorides within the structure, though, we know that there's going to likely be ongoing corrosion. And so it's really just a consideration of, do you want to just use your budget to repair and maybe plan on future corrosion, damage and repair and maintenance, or do you want to have a longer term repair? The one thing I didn't mention was, on the project case study for in Pennsylvania, the Wade Bridge, those sections of the structure are actually over a rail line. So in that situation, you don't want to, working over the railroads is hard enough, and you don't want to go back. And so some of those kind of external factors may come into play as well when you're looking at whether or not to use cathodic protection systems. But if you have chloride contamination in the structure at sufficient levels, repairing by itself may just be a short-term solution.
Fantastic. We have some questions coming in fast and furious, but this is going to be, unfortunately, the last one because we're at our time. What are your thoughts on using distributed anodes or anodes in general in new concrete applications, and what would be the expected service life of such an application?
Boy, we should do a whole seminar on new construction. That's a very interesting topic. We have used the distributed anodes in new construction, as well as discrete, back to like the XP type of anodes. And what you'll find is that there's two benefits. You have the period of time that the anode is functional, that's providing protection. But then, and that could be, it just depends on how long you design the anodes to last and what the environment is. But it could be, just say, from 10 to 20 plus years, you could still have active protection from a galvanic anode in a structure. But over that period of time, you have 10 to 20 years of current that's being generated to the structure. And what ends up happening at the cathode, which is the steel that's receiving the current, is that you're generating hydroxyl to steel, and it's actually providing I would say like a buffering to the steel to the future, so that even when the anodes are no longer functional, that there's still residual benefit to the structure. And there's some kind of theoretical kind of situations where you could provide such level of protection that you could achieve 50, 100-year service life of a structure even after the anodes are no longer active. Now, what we see probably from a practical standpoint is more common that you're using these types of anodes just in areas of high corrosion risk. So you may rely upon your normal concrete mix, et cetera, to provide, or membranes to provide protection. But you know that historically, maybe when you get over to the sides of the bridge where you have drainage, or like around joints, where those may be the areas where you first see future corrosion damage. And you can just target or selectively target those areas with anodes proactively, and just in those high risk areas. And that's probably the more common application for anodes in new construction, in my experience.
Fantastic. Thanks, Chris. We could spend the rest of the hour peppering you with questions, but I think we'll have to cut it off here. I apologize if we weren't able to get to your question here today, but I encourage you to reach out to Chris directly using his contact information right here. If you have any questions, whether it's about corrosion, concrete repair, or even the wonderful world of bourbon, I'm sure he'd love to hear from you. So thank you, Chris, for joining us for Webinar Wednesday today and for sharing your professional expertise and experience with everyone. On behalf of the Concrete Preservation Alliance and everyone in attendance today, thank you.
Thank you, Scott, and thank you for everyone for giving us a little bit of your time, and I really appreciate that.
Fantastic. So just a couple housekeeping notes here. For those of you who have not joined us before for Webinar Wednesday, before the Concrete Preservation Alliance is authorized to provide 1 hour of professional development credit for today's webinar. For those of you who are interested in receiving a certificate for that 1 hour of credit, you'll have to complete a very brief survey post-presentation. A link to the evaluation form has just been posted in the questions tab, so you can check it out there. Or there will be also the same link in the post-event email that you'll receive very shortly. Or you can use the QR code on the screen, just scan it with your phone, and you'll be taken to the form immediately. So just a reminder that today's webinar was recorded. Along with Chris's slides, they'll both be posted on the Concrete Preservation Alliance website at WeSaveStructures.info under the Events tab. Next up, we have pile protection for coastal bridges with our Floridian friend, Mr. Jason Chodacek, on Wednesday, November 11th, followed by targeted proactive protection for bridges with embedded galvanic anodes, as Chris discussed earlier, with our British brother, Mr. David Simpson, on Wednesday, December 9th. You can register for these and any upcoming webinars or events at WeSaveStructures.info. We hope you do. This brings us to the end of today's program. So thank you for spending your afternoon, evening, or night, depending on where you are in the world, with us. We sincerely appreciate your participation today, and we hope you'll join us in the future to save some structures. Be safe out there, and we hope to see you again very soon.